Okay, so today I want to speak about multi-party computation in the head because it's something that is really interesting and that has been seen a lot recently to create a signature scheme for post-quantum crypto. But I find that it's a little bit difficult to understand. And what is multi-party computation in the head? The idea is that now you have a prover and a verifier, and you want to do, let's say, zero-knowledge identification. And the prover is going to take this multi-party computation, and is just going to run it, what we call in its head, by emulating, like if we were running on a virtual machine. So he opens one virtual machine for every party in the computation, and then he lets them run the protocol that checks that the witness is correctly shared. And once he has done this, he looks inside every machine. What is your history? What have you done? What have you seen? What message? What have you done? And he just commit to what is called the view of what the people have done. And after that, the verifier says, okay, I want to check that you are not doing something weird. I want to check that what you have done in your head is indeed honest. So in order to do that, I take your commitment to what you have done, and I randomly ask for a few parties, or maybe all but one. That's what we will do later on. But you ask for some party, and you want to check what they have done. And in order
I'm going to talk about side channel attacks, physical attacks, not only side channel, but physical attacks, not about the attacks, but about protecting against these attacks, hardware and software implementations. And I'll mainly talk about a methodology that we developed with Vincent Ryman some years ago called threshold implementation, which by now is one of the most used techniques to protect against side channel attacks. So, in the 2005, I think, there was a paper who actually showed that all the masking schemes that were available by that time were broken when we consider hardware implementation. This has been discovered that the sharing, the masking don't work. And then in 2006, we proposed this other way of doing this masking in a way that the diversity cannot have a disadvantage, even when glitches are present. First, it was for first order DPA only, then we extended it to any security order. Then we, of course, tried to work on the efficiency and to use the minimum number of shares. And nowadays it is believed that it is proven actually that one of the properties, the main properties of TI, which is non-completeness, is a necessary property for every masking scheme.
Yeah, so I'm gonna present a searchable encryption scheme that together we made together with the with Marco Calderini, Riccardo Longo, and Massimiliano Sala. Searchable encryption, we can allow the remote server to perform some searches over our encrypted data on behalf of the client. But this without letting the cloud to know about what's the plain text, what the value of this encrypted data. So what's the idea or how is this is achieved? So we have our documents. From our documents, we extract some like keywords that characterize the document. And then using a searchable encryption scheme, we encrypt this keyword, so we produce some searchable ciphertext. Then we associate this searchable ciphertext with the encryption of our document. And then we store this in the cloud. And then if we want to perform a search, so we want to look for documents that are characterized by a keyword, then we take this keyword that we want to search, we generate a trapdoor, and we send this trapdoor to the server. And then the server, given the trapdoor and given all the searchable ciphertext that he has stored, he performs an algorithm called test, which is actually test whether this keyword is contained in the searchable ciphertext. And when he gets a positive answer, then he knows that this is a document that we are interested in, so he will just send us the encrypted document. So, to conclude, so with this scheme, we propose a searchable encryption algorithm that randomizes both ciphertext and trapdoor. And but if we swap the role of trapdoor and ciphertext, it means that also we swap the security level achieved by our scheme. So it means that we can achieve the highest value of security for the ciphertext indistinguishability.
Now, which is a hard problem, is to tell the true dimension of subfield subcodes, or by duality, the same problem is the true dimension of trace codes. What we know is this upper bound for the dimension of a trace code, which is very easy to see because you would take a basis for C, and then you take a basis of the large field over the small field, and you multiply these elements together, then you get a generating set for the trace code, but it is not necessarily linearly independent. And by duality, you get this lower bound for the dimension of the subfield subcode. I speak about maximum trace dimension, so we are interested in codes where for the trace code you have this you have equality here with this upper bound. There are many papers on the true dimension of subfield subcodes, but most of them focus for special construction. And our main result is the following. If C is a linear code over the large field Q, with Q to the M elements, and H is its singleton defect, so the difference of the left and right hand sides in the singleton bound, and we denote by P sub C the proportion of multiplier vectors A such that the linear code C sub A has maximum trace dimension. Okay, so we are interested in the probability that if you just take a random multiplier vector, what is the probability that the obtained code has maximum trace dimension, and here we have this lower bound for this probability.